theorem called Green's theorem. So Green's theorem told us that for two vector fields, P of x and y and Q of x and y, I'm sorry, these are scalar fields, not vector fields. Or in other words, two just functions of x and y. Green's theorem tells us that the integral of the quantity dq dx minus dp dy integrated over both x and y, so that's why it's a double integral here. And of course, this then defines some sort of area in the xy plane, right? So with whatever appropriate limits we need on the x and y integrals to specify a certain area A in the xy plane, that this area integral is equal to another integral, the integral of p dx plus q dy, integrated around the closed curve C, where that closed curve C is the boundary of the area A. Right? And we said that we were going to go around C in the counterclockwise direction. When we do this line integral right here. So that, in other words, another way of saying it as we go around, let's say here's the xy plane. Here's the area A, the area enclosed inside of that curve. So we integrate over that area, of course, in this integral. This integral, we integrate around the curve C that forms the boundary of A. Right? And as we go around C, we go around counterclockwise, or in other words, we keep the area A to our left as we go around. Okay? So again, this was Green's theorem. We proved it last time. And we are in the middle of looking at an example.
Professor?
Uh-huh.
If we went around clockwise instead of counterclockwise, would we just get the negative of the answer?
Exactly. Yeah.
Okay. So just.
So if you went around this clockwise, the result would be the same as minus this, or you could of course write that as this minus this, right? Just swap which one is subtracted from which in the integrand. Okay, so our example that we were kind of in the middle of is we said we wanted to find the work done by the force F, which is given by y squared x hat plus x squared y hat. And we're going to find the work done as this force moves an object around a closed curve C, which is given by this right here. We started at the origin. We go to the point 4, 0. From there we go straight upward along the positive y direction to the point 4, 2. And from the point 4, 2 we've come back to the origin along a curve, which I told you last time was the curve y equals the square root of x. And of course, notice that the point 4, 2 is along that curve, and of course the origin is along that curve also. Right? So this forms a closed curve. Right? There are 3 parts to that curve. Step 1, we said, is from the origin to the point 4, 0 along the x-axis. Step 2 is from the point 4, 0 to the point 4, 2 along the straight vertical line segment. And then step 3 was from the point 4, 2 to the origin along the curve y equals the square root of x. Okay, and so there were two methods we could do this. First of all, with method 1, which was the one we did last time, so I'm not going to go through the whole thing again. But along method 1, we said the work done by this force was the integral of f dot dr around a closed curve, right? That means the circle on the integral sign means a closed curve. By the way, let me remind you that we had already determined that this force was a non-conservative force. And remember that we know that for a conservative force, that the integral, the line integral, the work, in other words, for a closed curve, where we return to our starting point, is 0. So if this had been a conservative force, we would know just from that the answer was 0. But it's non-conservative, so the answer probably won't be 0. Anyway, so we can do it, of course, via this integral. F dot dr is f sub x dx plus f sub y dy. Right? Because f, of course, is f sub x times x hat plus f sub y times y hat. Dr is dx times x hat plus dy times y hat. So when we take the dot product of those two, this is what we get. And so we evaluated this, right? F sub x was equal to y squared. F sub y was equal to x squared. So this was the integral of y squared dx plus x squared dy around this closed curve C. And of course, we broke that up into the 3 different steps. We wrote this as the integral along step 1, equal sign, plus the integral along step 2, plus the integral along step 3. Same integrand in each of those integrals. I'm just being lazy and not writing it down each time. We evaluated this last time, and we found that the answer was 88/5. Right? So again, I'm not going to repeat all the work. This was, in a sense, a direct method. Right? We found the work directly as the integral dot product of a force and a displacement, and just did that line integral directly. Our second method, this is the one we didn't have time for last time, will be to use Green's theorem. Right, the integral that we did here on method 1 to find the work this integral looks like the right-hand side of Green's theorem. As long as we identify p, right, that's the coefficient of the dx, so p will be f sub x, in other words, y squared, and q is the coefficient of dy on the right-hand side of Green's theorem, so that's going to be equal to f sub y, or in turn, f squared. Okay, so by Green's theorem then, Green's theorem tells us that this line integral and this area integral are equal. So the work, instead of being written as this line integral, could therefore be written as the area integral instead. Right, so the integral of dq dx minus dp dy integrated over both x and y with appropriate limits of integration for the area enclosed inside of the curve C that we talked about back here. Okay? Okay, well, we know what P and Q are, so we can evaluate these integrals and plug them in. Right, Q is equal to x squared, so the derivative of Q with respect to x gives us 2x. P is equal to y squared, so dp dy is 2y. So we have a 2x minus 2y in the integrand, integrated over this area A. What's in the next step? Let's pull the 2 out in front. That'll leave just an x minus y in the integrand. Oops, and I forgot my dx dy here. And we need to think about what the limits of integration are going to be, okay? And tell you what I'm going to do here. I'm going to reverse the direction of the dy dx, and I'm going to put the dy with the sort of inside integral there, and the dx with the outside one. So I'll put square brackets around the inside integral. And my limits of integration. You know, you might be tempted to say x goes from 0 to 4, and y goes from 0 to 2. Can anybody tell me what the mistake would be with that?
Because y doesn't go all the way to it, it comes down as a function.
Right. If x went from 0 to 4 and y went from 0 to 2, that meant I'd be integrating over a rectangle. Right? That's not the area I have. At some value of x other than 4, right? Like maybe x equals 2 right here, my y integral doesn't go all the way up to 2, right? It only goes up to the top of this curve. And this curve is defined by this. So that means I can write my limits as follows. For a fixed value of x, okay, just think about the y integral, okay, or the inside integral in in the expression in the brackets that I have here. So for a fixed value of x, y is going from 0, right, that's the point along the x-axis, to the top of this curve, which is defined by y equals the square root of x. So that means my limits of integration should be from 0 to the square root of x on the y integral. Okay? And then on my x integral, I can put 0 to 4. Now, because my upper limit on the y integral is a variable, right? It's a square root of x. It depends on x in some way. That means I have to do the y integral before the x integral, right? Because when I do the y integral and I evaluate it at the limits of integration, which will be setting y equal to the square root of x at the upper limit, I'm going to get a result that depends on x from doing that. That has to remain part of my integrand for the x integral, right? Yeah?
Since we defined the path we're traveling is going counterclockwise, wouldn't our y be going from square root of x to 0?
I'm not going, you're thinking, I think, of the direction when I go around the curve, which I had to worry about for my method 1, my direct method. For method 2, I'm not really doing a direction. And it's just an integral over this area. I'm not following any kind of arrow or anything when I do it. Okay? Okay, so anyway, let's do this inside integral then. All right, we've still got a square root of 2 and a 0 to 4 and a whole dx from the outside integral. The inside integral, right? Since I'm now, again, we've got a function of 2 variables, right? Something that depends on both x and y. The usual thing when I do an integral like this, I'm integrating over y, treat x as if it's a constant, okay, when I'm doing this first integral. So I have an x dy, that will give me an xy, right, when I integrate with respect to y. And the minus y, when I integrate with respect to y, will give me a minus y squared over 2. And now I have to evaluate this, before I do the x integral, at the limits of integration. square root of x to 0. Okay, so we've got a 2 out in front. We've still got the x integral going from 0 to 4. Let's now evaluate this expression inside here at the limits of integration. Remember, y is being set equal to these things. It was y I integrated over in the previous step. So here I got x times, and now for y I'm substituting the square root of x. So that'll be an x to the 3 halves. Of course, 0 from the lower limit when y is set equal to 0. From this term right here, again from the upper limit, setting y equal to the square root of x, y squared will be equal to x. So this will be minus x squared over 2. And again, 0 from the lower limit when I set y equal to 0. Okay? Now I have just an ordinary single integral over x. So doing this integral, right, the integral of x to the 3 halves dx is x to the 5 halves divided by 5 halves, or in other words, multiplied by 2/5. And in the second term, I have a minus 1/2 already, and the integral of x squared dx will give me x cubed over 3.
Isn't it supposed to be x?
Minus x over 2.
Yeah.
Instead of x squared, it's just x.
Where?
Your square.
Oh yeah, here. Yeah, absolutely, you're right. I think I even said the right thing and I wrote the wrong thing. Right, yeah, because we plugged in y equals the square root of x, so y squared was just x. So this is just minus x over 2, and that means when we integrate that, right, we've got a minus 1/2 out in front, and the integral of x gives us x squared over 2. Okay, and then we still have to evaluate the limits 0 to 4. So from the first term, let's see, 4 to the 5 halves, 4 squared, which would be 4 to the 4 halves, is 16, times another factor of 2 is 32, right? So this is 2/5 times 32.
Why is it minus 1/2? Why is there 2 minus signs? Shouldn't there be only 1?
I think because there should only be 1. I think what
Okay.
happened is when I had the x squared over
Yeah.
2 and then a good x
Oh, you
cubed
did it
over
again.
3.
Okay.
And I think when I erased it, I didn't erase the minus sign, and then I wrote another one anyway.
Okay.
Okay, and from this limit, x squared from the upper limit is 16 divided by 4 is 4, so minus 4. We get 0 from the lower limits. And if you work this out, lo and behold, you will get 88/5. The same thing we got from method 1. Right? So, the point is, according to Green's theorem, that these two integrals are equal. We've just seen an example of that. It clearly works for this example. The advantage of this is that if, let's say you're doing, in fact, you could do any work problem, right? For any problem involving the work done by a force, right, as an integral of f dot dr for a closed path. We could have used the same kind of thing we did for method 1 here. In other words, f of x could be used as p and f of y as q. Then the integral for the work looks looks like the right-hand side of Green's theorem. So of course we could find the work directly just like we did with method 1 last time, but we could also then use Green's theorem to find the work as an area integral. I'm not going to write it out here, but in other words, use the left-hand side of Green's theorem. And just like we did for our method 2 right here. In this particular example, I don't think method 1 or method 2, I don't think either one was particularly easier than the other one. I think they were approximately equally difficult. But depending on what the functions p and q are, right, depending on what they turn out to be, it may be that one method is an easier integral to do than the other one. And so one advantage of Green's theorem is that you could use it to replace line integral that might be difficult, right? Of the form on the right-hand side here, you could replace it by the left-hand side by an area integral instead, which could turn out in some examples to be an easier integral to do. Okay, well, so I mean, this is an application of Green's theorem, but it's actually, to be honest, not the most important thing that we can do with Green's theorem. The most important aspect of Green's theorem for us is going to be that there are a couple of special cases of Green's theorem, which lead us to two other theorems, which you probably have seen in multivariable calculus when you took it, but if not, you're going to see them here. One is called the Divergence Theorem, and the other is called Stoke's theorem. And these are both special cases of Green's theorem, or things we can kind of get from Green's theorem, that are very important in their own right. Okay, so let's look at these special cases of Green's theorem. Okay, so let's start by thinking about a two-dimensional area that is, let's call it area A, that is bounded by a curve C, or to use your book's notation, your book uses this symbol, sort of a delta A, the same kind of delta little symbol that you use for partial derivatives. Okay? They'll often use that to reflect the boundary of whatever symbol comes after it. Okay? And that's a symbol that a lot of books use. So call it C or call it delta A, I don't care which. So here's some area A, it could be any arbitrary shape. Let's think about a point along the boundary of A like this, and let's draw a vector. We'll label it as dr that is tangent to the boundary of A at that point. Okay? Okay, that's an infinitesimal vector of infinitesimal length. So if we want to write it in terms of components, its components are also infinitesimal in length, so we can write it as dx times x hat plus dy times y hat. So this is, again, a tangent vector to the surface. Let's also define another vector at this point right here. This vector will make at right angles to the vector dr. So in other words, this vector points perpendicular to the surface at right angles to a tangent plane to the surface at this point. Right? So let's call that vector n hat ds, to use your book's notation. And my claim is that n hat ds is going to be dy times x hat minus dx times y hat. Let me convince you of those components in just a moment here. But this is an outward pointing normal vector. Normal meaning normal or perpendicular to the surface, or again perpendicular to the tangent plane. Right? A tangent plane at the point of this dot right here is a plane like this. So there could be two vectors perpendicular to that plane, either pointing that way, which would be pointing into the area A, or pointing this way, which would be pointing out. So that's the outward pointing normal. Okay? Now what about the components of this? Let's look at sort of a closer view here for a moment. Here's this point along the surface. Here's the dr vector that we've already drawn in. Move this up a little bit. Right, there's the dr vector. I'm claiming the dr vector has components dx and dy. In other words, if I define my x-axis horizontal, my y-axis vertical in the usual way, I could make a little right triangle like this, and this side of it right here would be dx, and that side of it right there would be dy. Okay? So what about this other vector, n hat ds? Right? It makes a right angle with the dr vector like that. So imagine taking that dr vector along with the triangle that it is the hypotenuse of, in other words, the two dashed lines along with it, and just rotating that whole thing as a rigid unit down so the dr rotates into the n hat ds. The other two sides of the triangle would be rotated like that. So in other words, there would be your dy and there would be your dx. Again, if I just rotate this down to that, and here, this is of course a right angle right there. So we can see from this diagram, right, if dx and dy are defined as the components of dr, that the components of n hat ds, well, right, points to the right, right, with a component, an x component, which is obviously dy, right, so there's the dy times x hat, and a y component, which is obviously dx, except it's pointing downward instead of upward, so it's minus dx, right, so there's the minus dx times y hat. Okay, so again, you can see that those vectors have those components. Now notice the way we've written this one. Right? Anytime we see a hat over something, it's of course a unit vector. So n hat here is defined to be a unit vector pointing in the direction of this vector. That would suggest that ds is the magnitude of this vector. And so the magnitude of this vector is clearly the square root of the x component squared plus the y component squared. So dy squared plus minus dx squared, well obviously that minus sign when I square it goes away. I can also of course change the order in which these two terms are added together. So I can write that as dx squared dy squared. Notice that's also the magnitude of this vector, right? Because if I again take the square root of the sum of the squares of the components here, I get that same thing. So this is also equal to the magnitude of dr. So both of these vectors have the same magnitude, right? Also notice that if I take their dot product, right, dr dotted into n hat ds. When I dot two things, I multiply their x components together, so dx times dy. And I add to that the sum of their y components, so dy times minus dx. So this is dx dy minus dx dy, which of course gives us 0. So the dot product is 0 because these two vectors are perpendicular to each other, which is of course the way we define them. So it's a good double check that if we take their dot product, we get 0. Okay, so those two vectors are going to come in useful in what we're going to do next. Okay, so I just wanted to define them so we can refer back to them. I mentioned we were going to look at special cases of Green's theorem. There are two special cases we're going to look at. Okay, so our first special case. Let's consider a vector field V, which has components Vx and Vy. Right, so Vx times x hat plus Vy times y hat. So this is in 2 dimensions, right? And let's let Q be equal to V sub x and P be equal to minus V sub y, and then use Green's theorem. Okay, well, Green's theorem, he told us that the area integral of dq dx minus dp dy integrated over both x and y from some area A is equal to the integral of p dx plus q dy over the closed curve C that forms the boundary of A. Okay, so let's think about what the integrand on this side is going to look like. Okay? So p dx plus q dy with p and q as we have chosen here will be minus v sub y times dx plus v sub x times dy. Well, I'm going to write this as follows. I'm going to write this as a dot product of two vectors. The first one will be vx times x hat plus vy times y hat, in other words, the vector v. And I claim if I dot that into dy times x hat minus dx times y hat, that will give me what I had on the line above. Just work backwards to see that this is true. Right, when you dot this into this, you're going to have this v sub x times dy. That gives you that term right there. Of course, this dotted into that gives you 0 because x hat and y hat are perpendicular. Similarly, this dotted into this gives you 0. This dotted into this gives you minus vy times dx, which is this term right here. Right? So you can see working backwards that this is true. Well, clearly this first vector in parentheses here is just the vector v as defined up here. And the dy x hat minus dx y hat looks like the n hat ds vector that I defined over here. Right? So this is actually v dotted into n hat ds. Right? Where again n hat ds is an outward pointing normal from our curve as we defined over there. Okay? So that's the right-hand side of Green's theorem. Let's look at what the left-hand side turns into with this assignment. So the integrand on the left-hand side is the derivative of q with respect to x minus the derivative of p with respect to y, with again q being v sub x and p being v sub y, this becomes the derivative of v sub x with respect to x minus a negative dv sub y with respect to y. The two minus signs, of course, cancel, so this is dv sub x with dx plus dv sub y dy. Well, that looks like the first two terms in the divergence, right? This is the divergence of v in two dimensions, right? Remember in Cartesian coordinates, the divergence of v is derivative of v sub x with respect to x plus the derivative of v sub y with respect to y plus the derivative of v sub z with respect to z. So this is the first two out of those three terms. If v sub y were equal to 0, if we have a two-dimensional function to begin with, like we do here, that is the divergence. Right? So in other words, it looks like Green's theorem is telling us in this case, the integral on the left-hand side of Green's theorem, we've analyzed that this right here turns into the divergence of v. So we're integrating the divergence of v over both x and y, integrating over some area A. And on the right-hand side of Green's theorem, that integral, well, the integrand from that is this right here. So this is going to be the integral of v dot n hat ds integrated around our closed curve C that forms the boundary of A. Okay. Well, this is actually the divergence theorem in two dimensions. There's actually a three-dimensional form of the divergence theorem, which I'm not going to really prove to you per se, but I hope I can convince you that this is true just by the, right here we're thinking of the area A as some sort of area in the xy plane, and the closed curve C as the boundary of A, right? But we can extend this to three dimensions. Okay, we can let's say tau be equal to some volume. Some books will call the volume V instead of tau, but I'm already using V to represent my vector field, and I think it might be confusing if we use the same letter to mean two different things, okay? So we'll call the volume tau instead. And of course, you've probably already seen d tau, or dv if you prefer, as a volume element. So for example, in Cartesian coordinates, this is dx times dy times dz. Right? In spherical coordinates, remember it would be r squared sine theta dr d theta d phi. Right? And in cylindrical coordinates, it would be rdr d theta dz, right? So remember that this includes, if you're doing some other coordinate system other than Cartesian, remember this includes those scale factors that we talked about back in chapter 10. Okay. So anyway, let's then use the symbol delta tau, kind of analogous to the delta A that we used over here. Over here we use the symbol to mean the boundary of A. So let's say that this is the boundary of the volume tau. In other words, it's the surface, right, forming that boundary. Right? In two dimensions where you have an area, you can think of the boundary of the area, the edge of that area as a curve, right? A line that goes around the outside. in 3 dimensions where you have a volume, you can think of the edge of that volume as the surface area that forms the outside of it, right? So that's what this means, right? So you might guess that in 3 dimensions, right, we're going to make this a triple integral now. We're going to take the divergence of V and we're going to integrate it over some volume, either d tau or dV, but again, I'd rather not write it as dV just because I'm already using V to mean the vector field whose divergence we're taking here. And whatever limits of integration reflect a particular volume, right, the volume tau, this volume integral is going to be equal to the integral of V dotted into n hat. I'll call it d sigma. I should have added one. Actually, let me add one more thing to this list, and I'll write the divergence theorem over here on the next area I'm freeing up here. So what I wanted to write here was that d sigma is an infinitesimal patch of area along the surface that I've called delta tau. Right? Delta tau is the complete boundary of my volume tau. Imagine a little patch along that surface, call that d sigma. So anyway, the divergence theorem in 3 dimensions then on the left-hand side, we have a triple integral of the divergence of some vector field V integrated over volume, d tau, with whatever appropriate limits of integration describe the volume that we want to integrate over, whether that's the volume of a sphere or a cube or a cylinder or something like that, for example. And on the right-hand side, we have an area integral. Right? So there's a V dot n hat d sigma. And we're integrating over the boundary of the volume tau, okay, whatever area that is. So, for example, if we're integrating over the volume of a sphere on the right-hand side, on the left-hand side, I'm sorry, then on the right-hand side we're integrating over the surface area of that sphere. If we're integrating over the volume of a cube here, we're integrating over the surface area of that cube over here, right? This is whatever the surface of that volume is. Right, so when we extend the divergence theorem from 2 to 3 dimensions, our area integral on the left-hand side now becomes a volume integral. Our line integral, an integral around a curve on the right-hand side, now becomes an area integral. Right? So that's why I put 2 integral signs on it. So again, I didn't prove to you that you can extend it to 3 dimensions, but hopefully it sounds plausible that you can. So this is going to be one special case of Green's theorem. Before we look at some examples of this, because we obviously will look at some examples to try to convince you, I'll evaluate both of these integrals for some specific examples and show you that we get the same answer both ways. But before we do that, let's look at the second special case, just because I think it's kind of useful to have them on the board at the same time. And compare what we're doing in the 2 cases. Okay, so for our second special case, we're actually going to do kind of what we did here, what we talked about doing here for a problem involving work. So again, think of a vector field V, which we'll write as V sub x times x hat plus V sub y times y hat. And now let's let Q be equal to V sub y and P be equal to V sub x in Green's theorem. Well, that's what we already said right here that we could do in any work type problem, like the example we did of Green's theorem right at the beginning. Notice that's the opposite assignment for P and Q for what we did in this case, right? Over here, we let Q be V sub x and P be V sub y, or minus V sub y. Now, it's vice versa, okay? And no minus sign, okay? Well, then the P dx plus Q dy that appears in the right-hand side, still got Green's theorem right up here on the board. So on the right-hand side, that was the integrand we had. So with this assignment for P and Q, this is going to be V sub x times dx plus V sub y times dy. We could write this as the dot product of two vectors. The first is V sub x times x hat plus V sub y times y hat. And we'll dot that into d sub x times x hat plus d sub y times y hat. Working backwards a step, you can see that this dot product will give you this result. And this dotted into this gives you the first term, this dotted into this, and this dotted into this gives you 0, and this dotted into this gives you this term right here. Well, and clearly the first vector here is v, and the second vector, dx times x hat plus dy times y hat, is what we defined as dr over here. So this is v dot dr. So that's the integrand on one side of Green's theorem. I'm going to put a box around Green's theorem here so we can find it easily to go back to it. We just evaluated the integral on the right-hand side, or the integrand on the right-hand side. Let's look at the integrand on the left-hand side. Okay. The integrand on the left-hand side involves the derivative of q with respect to x minus dp dy. Well, q is equal to v sub y, so this is the derivative of v sub y with respect to x. And p is v sub x, so this is derivative of v sub y with respect to x minus the derivative of v sub x with respect to y. Well, this looks like part of the curl of v, right? In particular, this looks like the z component of the curl of v. Right? The z component of the curl of v would involve this. Right? Or in other words, it looks like we could write this as the curl of v dotted into the z hat unit vector. Right? We take any vector and dot it into the z hat unit vector that picks off the z component of that vector. So in other words, Green's theorem, right, which again is in the form written over there, right? The original form of Green's theorem is that the area integral of dq dx minus dp dy, dx dy, integrated over some area A, is equal to the integral of p dx plus q dy over the boundary of A, or curve C as we called it. So now on the left-hand side, right, the integrand has become this right here. So on the left-hand side, we're taking the curl of v, dotting it into z hat, and then integrating over x and y. And on the right-hand side, we're taking v dot dr and integrating around, I'm just replacing C by the boundary of A. That's, again, those are two different names for the same thing. Okay? This is the two-dimensional version of Stoke's theorem, or Stoke's theorem in a plane is a better way of saying it. It's in fact, in particular, it's in the XY plane. Right? We were looking at an example here where A was some area in the XY plane. Right? And then the boundary of A was also in the XY plane. Right? Just went around counterclockwise. And notice that when we're doing that area we're integrating over in the plane, notice we're taking the curl of B and we're dotting it into a unit vector that is at right angles to that area in the XY plane. Okay? So we can generalize this one too, not to 3 dimensions like we did for the divergence theorem, but we can generalize it to a surface that doesn't necessarily have to be found in a plane. So let's I think your book uses sigma rather than A. Okay, so let's say sigma is some open surface. I'm using the term open surface as distinguished from a closed surface. Okay? When we were talking about the 3-dimensional version of the divergence theorem, we were talking, I'm sorry, about the 2-dimensional divergence theorem back here. In that, or actually, I'm sorry, the 3-dimensional version. Right, in the 2-dimensional version, this was a closed curve, right? Because it formed the boundary of this area A, and that means it had to be a closed curve. When we did the 3-dimensional version of the divergence theorem, we were integrating over some volume here on the left-hand side, and so the area integral on the right-hand side involved the area that formed the boundary of that volume. Notice that that area, delta sigma that I used to call here, is a closed surface. Right? It forms the surface of some sort of volume. So it's maybe the surface of a sphere, or the surface of a cube, or the surface of a cylinder. All of those are closed surfaces in the sense that they join back to themselves. Okay? What I'm talking about over here, instead, is an open surface. Okay? A surface that doesn't close back on itself, but it has some edge to it, or some boundary to it. Right? For example, here, right? This is not a closed surface. This is a surface that has an edge, and in fact, it's that edge we're integrating over on the right-hand side. Okay? So some open surface, as opposed to a closed surface, is what we're talking about here. But this surface does not necessarily have to be in a plane. It can be a curved surface, in other words, as long as it's not a closed surface. So it could be, for example, a hemisphere, right? Half of a sphere. It's curved, it has an edge, right? But it's certainly not a closed surface. Okay. So if sigma denotes some closed surface and then, some open surface, and then because it's open, it has an edge, so delta sigma denotes the edge of that surface sigma. We can write Stoke's theorem as the curl of B dotted into n hat d sigma, and we're integrating over the entire surface sigma there on the left-hand side. So that's what this has turned into now. What I'm doing is I'm saying our area doesn't necessarily have to be in the xy plane. can be any surface, and therefore the vector z hat that we dot this into, again, notice here, this was perpendicular to the xy plane. So I'm generalizing it to write an n hat instead of a z hat, where the understanding is that n hat is a unit vector, right? We know that because of the hat, of course, that is perpendicular to the surface sigma. And of course, there are two possible unit vectors perpendicular to a surface. I'm going to pick the one that points outward, and I'm putting that word outward in quotation marks because if we have an open surface, it's maybe not obvious what we mean by outward. Okay? But I'll come back to that in a minute. Let me just write the other side of Stoke's theorem. The other side involves v dot dr integrated around the closed curve that forms the boundary of my surface sigma. Okay, so this is Stoke's theorem. So, for example, you could have, like I said, maybe a hemisphere. Right, there's the top half of a sphere. So sigma could be this hemisphere. Again, it's not a flat surface like we originally had for our original version of Stoke's theorem, but we can still use Stoke's theorem for this. And so when we are evaluating on the left-hand side here, let's say we take a little infinitesimal patch of surface right there, okay, right along the edge. Then the n hat unit vector is going to point like that, okay? For a patch over here, the n hat unit vector points like this, okay? It's always pointing perpendicular to a tangent plane to the surface at that point. Now, if I said you're pointing outward, but actually I don't have to point outward. In fact, maybe I should even erase this because it's perhaps misleading. So, again, if we're looking at this case, if we take n hat to be, quote, outward, again, since our surface is an enclosed surface, there really isn't an in versus out. But, you know, often you can sort of think of this as outward, imagining that if the other half of the sphere were there, the bottom half of the sphere were there, then clearly I'd picked n hat to be in the outward direction. The thing to remember, though, that's important, is that whatever direction I take n hat to be here, the direction of n hat has to be related to the direction that we go around the curve on the right-hand side by the right-hand rule. So in other words, if I pick my n hats to be in the direction I have shown in this sketch here, then I have to go around the boundary, right? The boundary of this surface. If sigma is this hemisphere, then the boundary of it is this line, the equator, if you will, if you want to think of this as, you know, like the northern hemisphere of the Earth, right? It would be this circle that forms the edge of it. And I'm saying if we pick n hat in the direction that I have shown here, we should go around this edge, delta sigma, when we do this integral here, this line integral, in the direction that I have shown with the arrows here. So the right-hand rule, the way that comes in, is if I put my fingers of my right hand curling in the direction of those arrows, then my thumb gives me more or less the direction of n hat. I mean, my thumb is actually up, but of course a little patch right here at the top would have n hat up. So basically that would tell me, at least for that top patch, n hat has to be up rather than down. And then just imagine it continuously turning to the side a little bit as you look at other patches over here or over here. Okay? Now, you are perfectly okay in doing, for example, for that hemisphere, you are perfectly okay doing it like the way I just showed you. In other words, n hat will point more or less up, and we go around the curve for the line integral this way, or we could go around this curve here the opposite direction, but then by the right-hand rule my thumb is pointing down, and so now n hat points downward there, sort of inward like this, in this direction, inward like this, in this direction. So we can do it either way, as long as we are consistent. Okay? So just remember that the direction we proceed around this curve when we do this line integral and the direction of n hat here have to be related by the right-hand rule. There's two ways of doing it. Both ways are okay. Okay? But you have to, you can't do, you know, the arrows down here in this direction and the n hats here are pointing in this direction. You have to either stick with that picture or that picture. Okay? Okay, so that's Stoke's theorem. So notice that both the Divergence Theorem and Stoke's theorem are both special cases of Green's theorem. They're both derived from, or at least sort of derived. I mean, I maybe skipped a little bit of a step here when I extended it to 3D, but at least a two-dimensional version of the Divergence Theorem and Stoke's theorem in a plane, at least, were both special cases of Green's theorem. And then we both kind of generalized them both a little bit beyond that point. I do want to point out to you that all of these theorems, Green's theorem, Divergence theorem, and Stoke's theorem, all will work for any coordinate system. Okay? We wrote down a few things in Cartesian coordinates, like right here, for example, when we were evaluating them, but they are true in any coordinate system. Okay? So there could be examples where spherical or cylindrical coordinates are involved also. Right? They're true in any coordinate system. So let me give you an example of each of them. Okay, so as an example of the divergence theorem, let's consider this vector field. X times x hat plus y times y hat plus z times z hat. We could either write it this way in Cartesian coordinates, or equivalently, we could write this as r times r hat in spherical coordinates. Same vector field either way. So let's find the volume integral that appears on the left-hand side of the divergence theorem. We won't always write three integral signs, but it's understood that d tau means a volume, Right? So even if we don't put 3 integral signs, it's still understood that this is a volume integral. Okay? And we're going to use tau to be a sphere of radius capital R, centered at the origin. And of course, that means that for any point inside of tau, inside of this volume, x squared plus y squared plus z squared has to be less than capital R squared. Okay? Remember, the equation of a sphere would be x squared plus y squared plus z squared equals R squared. Right? So that would be a point whose coordinates x, y, z satisfied x squared plus y squared plus z squared equals R squared would be on the surface of the sphere. So if x squared plus y squared plus z squared is less than R squared, this is a point on the interior of the sphere. Okay? Okay, so if we want to evaluate this, the first step is to evaluate the divergence of V. We can actually do that either in Cartesian coordinates or spherical coordinates. If we did it in Cartesian coordinates, it would be the derivative v sub x with respect to x, plus the derivative v sub y with respect to y, plus the derivative of v sub z with respect to z. Well, v sub x was x, v sub y was y, v sub z was z. Each of these derivatives is 1, so the divergence of v is 3. Okay? We can also use spherical coordinates to analyze the divergence of v. Right? In spherical coordinates, the divergence is 1 over r squared times the derivative with respect to r of r squared v sub r. There are some other terms which I don't have written in here in my notes, but we've seen them before, right? We found the divergence in spherical coordinates. There are 2 other terms that involve derivatives of v sub theta with respect to theta and v sub phi with respect to phi. But notice that in our case, in spherical coordinates, we only have a radial coordinate. We don't have a term involving theta hat or phi hat. So in other words, v sub theta and v sub phi are 0. With v sub theta and v sub phi equal to 0, we know the other 2 terms would be 0 anyway, so this is the only term we need to worry about. V sub r is the coefficient of r hat, so it's just r. So r squared times r is r cubed. The derivative of that with respect to r is 3r squared. And then we divide by r squared up front. So again, we get 3. So whether we evaluate the divergence of v in Cartesian coordinates or in spherical coordinates, either way we get the same answer, namely 3. Okay? So anyway, then the integral that we want to evaluate is the integral of the divergence of v d tau over the surface of this, or I'm sorry, over the volume of this sphere. Well, the divergence of v was just 3. That can, of course, be pulled out in front. So 3 times the integral of d tau. We have to use spherical, or we should use spherical coordinates. At this stage we evaluated either way, Cartesian or spherical, but at this point it's going to be much easier to use spherical coordinates. In spherical coordinates, the volume element d tau, or dv as we called it earlier, is again r squared sine theta dr d theta d phi. At this point, we should put 3 integral signs because we are writing 3, d somethings. And we should put limits of integration for each of those, telling us phi goes from 0 to 2 pi, theta goes from 0 to pi, and r goes from 0 to capital R, to cover the entire volume of our sphere. So we got a factor of 3 out in front. Since there's no phi's in the integral, in the integrand, the integral of d phi gives us phi, evaluated from 0 to 2 pi gives us 2 pi. We have the integral of sine theta d theta. That one goes from 0 to pi. And we have the integral of r squared dr. That one goes from 0 to capital R. Well, I'll let you double check this one, right? The integral of sine theta is minus cosine theta evaluated at the endpoints. Let you check that that gives you 2 if you do that. And of course, this one gives us capital R cubed over 3. That 3 cancels with the 3 out in front. So we have 4 pi capital R cubed. Notice that this is just 3 times the volume of a sphere of radius capital R. And actually, if we'd realized that up right here, we could have saved ourselves a little bit of work. Right? D tau integrated over tau, the volume of the sphere, is just going to give us the total volume of the sphere. In other words, 4/3 pi r cubed, and then the 3 in front cancels with the 3 and the 4/3. Right? So we could have skipped a little bit of work if we'd realized that at that point. Okay, so anyway, that's our answer, is 4 pi capital R cubed. We did that by evaluating this integral right here. Okay? We want to check the divergence theorem. So according to the divergence theorem, that integral, which we just evaluated, which is the left-hand side of the divergence theorem, should be equal to this integral, right? The one on the right-hand side of the divergence theorem. So let's calculate that one too, and see if they are equal. Okay, so to evaluate v dot n hat d sigma over the boundary of tau, right, so we're going to evaluate this over the surface of that sphere. Well, we already have what v is, right? V is over here. But to evaluate this, we need to think about what n hat is and what d sigma are. Okay? So remember that if we have some function of x, y, and z being constant, for example, x squared plus y squared plus z squared equals capital R squared. We know that that's true on the surface of the sphere. Right? That's the equation of the surface of a sphere. And R is a constant, right? So R squared is a constant. So on the left-hand side, we've got some function of x, y, and z, and we're setting it equal to a constant on that surface. So anytime we have some function being set to a constant, right, if this is the equation of the surface, that surface delta tau, like it is in this case, then remember that the gradient of f is perpendicular to the surface. And if we think back to when we first started talking about the gradient, we talked a little bit about topographical maps as an example, right? And on a topographical map, we might have some kind of curve like this along which the elevation as a function of x and y, your position along the surface of the earth, the elevation is constant. Everywhere along this line is the same elevation as every other point. Right? And so along this contour line, we said that the gradient, if we call f the thing that's constant, the elevation, the gradient of f was pointing in the steepest uphill direction. Right? And that made a right angle to the actual contour line. So again, if f, like the elevation in this case, is some constant along that curve, think of this as now a two-dimensional surface instead of just a line. But the same conclusion is true. If we take the gradient of f, we get a vector that is pointing in a direction perpendicular to that surface. Okay? So, in our case, think of f as x squared plus y squared plus z squared. Again, this is a constant, namely r squared on the surface. So the gradient of f, which of course we get by taking derivative of f with respect to x times x hat plus df dy times y hat plus df dz times z hat. So right, for this f, this is going to give us 2x times x hat plus 2y times y hat plus 2z times z hat. Or, of course, 2 times the quantity x times x hat plus y times y hat plus z times z hat. So this vector is perpendicular to our sphere, to the surface of our sphere. Well, notice that this gradient of f has a magnitude equal to the square root of 2x squared plus 2y quantity squared plus 2z quantity squared. In other words, the square root of the sums of the squares of the components. Right? And of course, the 2 squared gives us a 4 in each of those terms. We can pull that 4 out in front. In fact, we could pull it out in front of this square root, at which point it turns into a 2. So this is 2 times the square root of x squared plus y squared plus z squared. Or in other words, 2 times capital R. Right? Because on the surface, if we're evaluating this on the surface, we know that for any point along the surface, x squared plus y squared plus z squared equals capital R squared. Okay. So therefore, n hat was the vector I wanted to find before I can finally evaluate this integral up here. N hat is a unit vector, right? We can make any vector into a unit vector by dividing it by its own magnitude. So let's take the gradient of f. We already know that points in the right direction, right? It points perpendicular to the surface, and divide it by the magnitude of the gradient of f. That way we get a unit vector that points in the same direction as the gradient of f, namely perpendicular to the surface. Okay? So the gradient of f was 2 times x hat plus y hat plus z hat. And we're going to divide by the gradient of f, or the magnitude of the gradient of f, which worked out to be 2 times capital R. Okay, so the 2's cancel. Now, all of this would have been so much easier in spherical coordinates, but let me just finish showing you in Cartesian, and then you can see how much easier it would have been in spherical coordinates. So v dot n hat then, right? The integrand in this integral right here. Is going to be v sub x times x hat plus v sub y times y hat. Wait a minute. So v, I'm sorry, v was defined as x hat plus y hat plus z hat to begin with. So in other words, v sub x was equal to x hat. Or I'm sorry, v sub x was equal to x. And v sub y was equal to y. And v sub z was equal to z. So v is really x times x hat plus y times y hat plus z times z hat. And we're going to dot that into n hat, which is now this vector down here, namely x times x hat plus y times y hat plus z times z hat, all over capital R. Well, we've got a 1 over capital R, I'll move that out in front. And when we do this dotted into this, we'll get x squared plus y squared plus z squared, which is, of course, the same thing as r squared. And we've still got the 1 over r out front, so this just works out to be capital R. Like I said, it would have been much easier to do this in spherical coordinates. In spherical coordinates, we've got our sphere centered at the origin. We're at this position on the outside. Our n hat vector that points like this is clearly just the same as the r hat vector. Right? It points radially outward in spherical coordinates. So in spherical coordinates, we could say v dot n hat is equal to r times r hat. That's what v was in spherical coordinates, as we said over there at the beginning. And that gets dotted into r hat, because that's what n hat is in spherical coordinates. So this just gives us r, but we have to evaluate this at the surface. Perhaps I should have written that explicitly right here. This is where we did this right here. When we did it in Cartesian coordinates in terms of x, y, and z, it was at this stage here, right? We said that x squared plus y squared plus z squared, if we're on the surface, is capital R squared. Okay? Well, here, if we're at the surface, little r gets replaced by big R, because that's the value that little r has if we're on the surface. Okay, so in any case, either way, whether we do it in Cartesian or in spherical coordinates, v dot n hat at the surface is equal to capital R. And so the integral on the right-hand side of the divergence theorem, this integral right here, is right, v dot n hat is just r, so r d sigma. And we should write out what d sigma is. Again, the easiest thing to do is spherical coordinates. So I've got a capital R out in front here that appeared before the d sigma. D sigma is a patch, an infinitesimal patch of surface area in spherical coordinates. And you know the easiest way to write that this expression here for d sigma is basically like the expression for d tau or dv, a volume element in spherical coordinates, but with the dr left out. Because dr implies that r is changing, and we would be covering a volume, not just a surface. If r were changing, we're staying on the surface, r is remaining fixed. And the other piece of it, I guess, right, the volume element d tau in spherical coordinates we would write as little r squared times sine theta dr d theta d phi. So again, I've left out the dr, but the other thing I've done is I've taken the little r and set it to equal to big R, because that's the value little r has when we're on the surface. Okay? So it's just like the volume element, but with the radius set equal to the constant value it has. It's no longer a variable, and therefore the dr, again, gets left out. Okay, and now I'm integrating over theta and phi, so my limits again go from 0 to 2 pi on the phi integral and 0 to pi on the theta integral. Okay? So there's an r cubed, which I can bring out in front, right? That's a constant. So there's a sine theta d theta from 0 to pi, and a d phi from 0 to 2 pi. This last integral is, of course, equal to 2 pi. This one right here is equal to 2. I'll let you double check that. So the bottom line, right, we've got 2 times 2 pi times r cubed, or in other words, 4 pi r cubed is our answer. Okay? And so notice that both sides, we've evaluated both sides of the divergence theorem. We've evaluated the divergence of V, integrated over the volume of this sphere, and we got 4 pi capital R cubed. We also evaluated V dot n hat d sigma over the boundary of this sphere, in other words, the surface area of the sphere, and we got 4 pi cubed that way, 4 pi r cubed that way also. So we, of course, expected from the divergence theorem that these results should be equal, and they are.
Should one of those have a double integral in it?
You can write this one as a double and this one as a triple if you want.
Okay.
Because this is we're integrating over a volume, and we often will write that with 3 integral signs, so you can put them there if you want. And you can put 2 on this one because we're integrating over an area. But again, I think I mentioned this before, we often don't bother writing those extra integral signs because it's understood that tau is a volume and sigma is an area. Okay? But if you want to write them, you can. Okay, let me just make some comments about notation here. So anyway, I mean, we've evaluated both sides of the divergence theorem for this example and shown that they're equal. But let me point out that if we hadn't been asked to evaluate both sides, maybe we'd been just asked to evaluate one side, if we thought that using the divergence theorem and replacing the integral we were originally asked to evaluate, replacing it by the other integral that the divergence theorem says it's equal to, if we think that that will give us an integral that's easier to do than the one we started with, then we've saved something by doing that, right? And we can use the divergence theorem to allow us to do that kind of replacement. I said I was going to make a comment about notation. Different books use different notations, and it's possible I may lapse from one into the other too, although I'm trying to stick with what our book uses. So let me just make a few comments about this just to try to avoid confusion. So we will typically use right? Tau or V to represent a volume. I'm trying to stick with tau because that's what your book uses. But some books will use V instead. Again, the reason I didn't use V is I was using the vector V to represent our vector field, and I wanted to avoid some possible confusion because of that. Okay? And then anyway, the d tau or dV is an infinitesimal volume element. I've used d sigma, but some books will use dA to be an area element. Right? A patch of area on the surface. N hat I've used to stand for an outward pointing normal vector at the surface. And I referred to, in this integral right here, notice I had an n hat d sigma. Some books will define this to be a vector d sigma or a vector dA. Right? Remember we used d sigma or dA to mean the same thing. So our book uses this notation. In other words, they use d sigma as a scalar, right? A patch, infinitesimal patch of area along the surface, and n hat as this outward pointing normal vector. But some books will define d sigma or dA, depending on which of these notations they use for it, to be a vector. Okay? They will say it's a vector whose magnitude is the infinitesimal patch of area, but whose direction is assigned to be the same direction as the n hat vector. In other words, a pointing outward normal to the surface. Okay? So again, when you look at different books, right? If you look at a book that uses this kind of notation or this kind of notation, they might write the divergence theorem. Right? Here's the divergence of V integrated over volume on the left-hand side. On the right-hand side, instead of writing a V dot n hat d sigma, they might write a V dot dA. Right? Integrated over an area A that forms the boundary of the volume V. So this is an alternate way, just alternate notation for the same thing. Okay? And again, different books use different notations, so you might run across this if you look somewhere else. There is a similar possible confusion in the notation. This was the notation for the divergence theorem. In talking about Stoke's theorem, there are also some questions of notation that vary from book to book. So for Stoke's theorem, you will see both sigma and A used to designate an open surface. D sigma or dA would be an area element, in other words, an infinitesimal patch of area along that surface. N hat is again a normal unit vector to the surface. In this case, since our surface is an open surface, I can't really designate an outward pointing normal as opposed to an inward pointing normal, as I talked about over, I guess I've erased it, but I had a picture over there a little while ago saying you could use either one. Right? And then d sigma or dA, or sometimes it's just called a curve C, will designate the closed curve that forms the boundary of our area A. Or sigma, whichever you prefer to call that area. And then the dr, I think, is what I called it. It's not on the board anymore. But some books will call it ds or dl. This is an element of length along the curve C or delta sigma or
Delta.
oh, I'm sorry. I don't want to call it. That's not delta. We'll just call that okay, I think I had did I have a D or a delta there? I don't know, it should be a delta in any case. So the curve C or delta sigma or delta A are all names for the same thing. So an infinitesimal element of length along them, different books will use those possible sets of notation. Again, I'm trying to stick with the dr because that's what our book uses. So again, Stoke's theorem tells us that the curl of V dotted into n hat d sigma or dA. And by the way, some books will use this same notation also. They might refer to this as a vector d sigma or a vector dA. Anyway, Stoke's theorem tells us that this is integral equal to the integral of v dot dr or dl or ds, whichever of those symbols you prefer. This integral is over the area sigma or area A. This is over the curve C or delta sigma or delta A that forms the boundary. Okay. And as I mentioned before, there's an ambiguity here. You could either take the n hats to be outward, quote unquote, like that, in which case the line integral around the boundary that we do on the right-hand side here goes in that direction, or I talked about a hemisphere before as an example of a surface. This is just sort of a distorted hemisphere. If you take inward, quote unquote, pointing normals, as indicated like this, then you would have to go around this surface in the opposite direction. Again, the direction of the n hat unit vectors, or equivalently the d sigma or dA if you want to define the vectors that way, and the direction we go around the curve C or delta A in evaluating the integral of v dot dr around that curve. The direction of this unit vector and the direction we go around in evaluating this are related by the right-hand rule. Okay, as I mentioned before. There are also a few other conditions that have to be met for Stoke's theorem to work. Okay? One is this surface sigma, or A, whichever you want to call it, can't have any holes in it. In other words, it must be simply connected. sigma, or C, whichever you want to call it, must be a closed curve. After all, a curve that forms the surface of a boundary of an area must be closed, right? It's gonna loop back and join onto itself. But it also can't cross itself. So it can't be like a figure 8 type curve, for example. Okay? And the third condition here is that our surface sigma must be two-sided. In other words, it can't be a Mobius strip. Everybody know what that is? Okay. Just in case you don't know what it is. If I take a piece of paper and I join these two ends together, but I twist one like this first and then glue these together, this is a Mobius strip. Okay? This is not a two-sided surface. This is only a one-sided surface. Because let's take this pen and let me start drawing along this surface like this. And I keep going around. And if I can get this thing to write.
Oh, the illusion's gone.
There we are, back again where we were. I follow along the surface and I just keep going, and if I didn't have to move my pen off the paper because my arm won't go through, I can get right back where I started from without ever taking my pen off the paper. Okay? In other words, if I go around one side, because of the twist in the paper, as I come around, when I first followed around like this and I came back here, now I was on the opposite side of the paper from the side I started with, and I just had to go around once more, and I was back on the same side I started with. The problem with a surface like this is that we can't decide which side of it is which. Okay? This thing is going to be screwed up, right? There will not be a unique choice for n hat, for the direction of n hat, and how it's related to how I go around the edge of a surface. Okay? So I can't have any kind of weird surfaces like that. Now, actually, I should point out that we can apply Stoke's theorem to a closed surface. Right? We originally talked about Stoke's theorem for an open surface. Right? But Stoke's theorem actually is true for a closed surface. It's not that it's not true. It's just not very interesting. Both sides of the equation are just zero in that case. Okay? Both of the integrals are equal to 0 in that case. Okay? If you take the curl of a vector field and dot it into and have the sigma vector and integrate over a closed surface, you will get 0. I'll show you an example of that next time. We're out of time today, obviously, so I'm not going to be able to do it now. I think it's obvious looking at the right side that it's going to be 0, because if you have a closed surface, the curve that forms the boundary of that surface, the delta sigma, the curve that we're integrating over here, shrinks to 0. Right? Think of an example where maybe you were applying Stoke's theorem originally to an open surface that consisted of most of a sphere, except that instead of maybe being, well, actually originally start thinking of a hemisphere, like we were talking about originally in this example of it. And then your v dot dr integral is integrated around this curve right here that forms the boundary. Okay? So imagine instead of just having a hemisphere, you now had some of the bottom hemisphere also. So you had all of the top and most of the bottom, but you were just missing a little hole. right down there at the bottom. Then when you did your surface integral, you'd be integrating over the surface of that almost whole sphere. And when you did the line integral right here, you'd be integrating just around this little thing, right? And now imagine that you included the entire sphere in your area integral on the left-hand side of Stoke's theorem. Then basically the line integral that you do on the right-hand side, you'd be doing it over a curve that's shrinking down to 0, right? Something that shrinks down and has 0 length. And I think it's obvious that that's going to make this integral on the right-hand side 0, right? And so you could apply Stoke's theorem to a closed surface. It's not that it's not true for a closed surface. It's just not that it's just that it's not very interesting. Both sides of it are 0. So the place that it's useful is for an open surface. But it is true for a closed surface too. Again, it's just not very interesting. Okay, I was hoping to do an example of Stoke's theorem today too, but we obviously are out of time, so we'll do it next time. I do have a couple of homework ones here. I returned homework one about a week ago, but some of you weren't here the day I handed it back, and then I forgot to bring the ones that I didn't hand back the next time.